And now we move to the other end of the world. We have a talk, experimental talk by Janne Pakarinen from Jyväskylä. He will talk about nuclear spectroscopy with recoil separators at his laboratory. Janne, please allow 5 minutes for questions at the end of your talk.
Yes, I will. Do you see my slide now and you can hear me all right?
Yes, we can see your slides, we can hear you.
So thanks for the organizers. This is a real opportunity for me to present the microphone open still. Yeah, so essentially I'm presenting the work we have done in Jyväskylä using 2 different recoil separators, and I'm presenting indeed the work that has been done with the whole group. So there is very little of my own slides here, so I will be grateful for the people's efforts here. So this is the outline of my talk. I will briefly tell you, because there is probably some people in the audience who don't know where the Jyväskylä is. I will briefly show our facility and then go into more details what our nuclear physics spectroscopic group is doing in our physics program. I will briefly do the instrumentation presentation and then show some recent highlights from both different separators. And then finally, I will end up showing a couple of slides related to our future prospects. So as a side, since there are probably people who are not aware of our laboratory, I will start with the presentation of the lab. So if you are arriving from space, this is the video how it would look like. We are, I think we are the most north accelerator laboratory in the world. We have a very beautiful location by the lake. And as you see, this is not live, although it could be. We have already dark here. I should say that it's a great pleasure for me to be here, since this is exactly the same time zone that you have there in the South Africa. This is the layout of our laboratory. We have 4 different accelerators. In fact, these 2 devices here, Pelletron and C-Linac, which is essentially a racetrack electron device, they are used for application purposes. Then we have a small cyclotron called MCC30. This is serving IKISOL facility that is shown here on the top. And some of you who might have been earlier listening to talk by Maria, she was presenting boron 8 work, and that was done at IKISOL. But the main workhorse of our laboratory is this K130 cyclotron that is delivering beams for several different experimental stations here. Our group is working with these 2 separators. The one on the left here is called RITU, and the new one here on the right-hand side is MARA. And this is now zooming more in, showing them from the different perspective. On the left, there is MARA, a separator behind the EUROGAM array here, which can be actually moved between the 2 caves. And on the right-hand side, you see the RITU separator. Before going to an experimental program, I want to introduce our group. We have 7 permanent researchers, in total around 20 group members. I should point out that much of the work is being conducted by our postgraduate students and postdoctoral researchers. And at the moment we have 3 people having emeritus status. Many of you know Matti Leino, Rauno Juli, and Sakari Juutinen. So the major physics themes that our group is involved in, or focusing most of the work, can be divided in 4 different disciplines. First of all, we want to provide, for example, solid configuration assignment in odd mass transfermium nuclei using combined electron and gamma-ray spectroscopy. This is the very heavy region in the chart of nuclei. We study the shape coexistence in neutron-deficient lead region. We, for example, want to confirm the existence of 3 different shapes in the same nucleus and relate the collective phenomena to emerging data on radii and masses. Then moving on towards lighter nuclei, we want to study short-lived proton unbound states at the proton trip line, and we also want to extend studies of physics at the n=z line towards heavier nuclei. This involves neutron-proton pairing, Bloch energy differences, and super deformation at n=z at 40 region like here. We also want to study the structure of nuclei on the island of alpha decaying nuclei just above the tin 100. This is also relevant for the RP process, which terminates around tellurium 104. So what is common in all these regions is that they are located on the left from the value of stability. And finally, to highlight how this research program has been established, I'm showing a plot where I'm actually plotting the number of measurement days per nucleus along the chart of nuclei. So the peak here is actually nobelium-254. That was once a major discovery and resulted in a Nature article. Nowadays, we can consider nobelium-254 as a, for example, commissioning nucleus to commission new devices or even calibrations. So if one wants to show scientific output, you can use many different kinds of metrics. So here I have chosen in the first example, the measurements, how we have been doing over the years. So since 2003, we started, of course, we've been running for longer, but this history is only covering from 2003. So we have been running around 11 experiments a year. And concerning this year, maybe around 65 days are foreseen. And as you can imagine, this decrease is down to basically 2 facts. First of all, of course, the corona pandemic has reduced the number of experiments that we've been able to produce, but we also had a fairly, well, we have 2 months maintenance break in the beginning of the year. So under these circumstances, I think 65 days is a remarkable achievement after all. And we are typically running in campaigns, which is highlighted here or illustrated here. And as you can see, we have been running fairly consistently. There have not been long breaks at all. And one thanks to this is essentially the stable operation of the K130 cyclotron. So another way of showing the scientific output is, of course, the number of publications. So here I'm plotting them by year, and there is no big dips seen, and showing some sort of a consistency what we've been doing lately over the years. So the main technique that we are using is the recoil-decay tacking, which I'm illustrating in this slide. So if you consider that the beam is arriving from the right, here with the laser pointer, we have the production target in the middle of the EUROGAM 3 array. Let's consider when the beam hits the target as a time 0. We can perform prompt spectroscopy there. Then the fusion-evaporation residues, which are the nuclei of interest, fly into the MARA separator. MARA is a vacuum mode separator, which essentially is a mass separator that separates the primary different masses from the primary beam before recoil is being implanted at the focal plane for identification and decay spectroscopy. So this happens roughly half a microsecond after the impact at the target position. So there we can at the focal plane wait for some time and allow for the recoils to decay, and then we can identify them based on the different decay modes. So the recoil-decay tacking technique is very powerful, and one reason for that is that some of the nuclei of interest indeed decay via characteristic emission of alphas. So we have a very versatile focal plane setup. The gamma-ray detectors we can include there are for example, 6 Clover detectors or 3 new beta detectors that we have put in there lately. In this schematics, we have Clover detectors around. We can also replace the 2 back detectors with the 1 big great Clover detector. In the heart of the whole focal plane setup, there is the implantation detector, Micron BB20, which is a double-sided silicon strip detector, which allows for, thanks to high granularity, it allows for the good tracking of each recoil with a certain recoil that was implanted. We can also put the planar detector back, and there is also a time of flight measurement. There is a gas detector slightly upstream from the implantation detector that is here in the focus of the germanium detectors. And then we can also have some other ancillary detectors included. So if the RITU and MARA separators form the backbone of our experimental campaign, correspondingly important tool is the EUROGAM Ge spectrometer, which is shown here. In principle, there is nothing new in JUROGAM Ge related to JUROGAM 2, apart from the fact that it can be moved between these 2 separators without being switching off the power. So that essentially means that we can run back-to-back in-beam gamma-ray experiments between these 2 separators. If we had to switch off the detectors, it would mean that they would see, all the time when we are running experiments with these detectors are prone to the neutrons that can then cause neutron damages in the germanium crystal. So if you switch off the detectors, and the neutron damages will appear, and you have to anneal the detectors. So in order to have continuously running setup, we want to keep them powered up all the time. So therefore, this EUROGAM Ge array was built at first place. So in the top right corner, you can see some of the statistics that we have done recently. Another important device that we use in beam is the so-called JUTube Charge-particle detector. It combines 120 plastic scintillator elements, which are read out by silicon photomultipliers. And I should point out that the evaporation, that the veto efficiency for 3 proton channel is very high, 97% veto efficiency for that. This will be published later by Panu Ruotsalainen and others. And here I'm showing one important device as well. It has not been used so far with MARA, but my research team is working hard in order to make it happen soon. So this is the SAGE device that essentially is the first serious attempt to combine high-efficient gamma-ray detection together with the high-efficient conversion electron detection. And indeed, this will be set up for a campaign early next spring. All right, so then I will show couple of selected recent highlights. I will have one slide showing what we have done recently with RITU and one with MARA, and then a couple of examples from in-beam work. So we have produced new nuclei at RITU quite recently. These have been published. So for example, I'm now highlighting here the region of very heavy elements, and there are 2 new isotopes that came out from this experiment by Jonas Konki and co-workers, namely 240 einsteinium and 236 berkelium. And here our findings extend the systematics of the einsteinium and berkelium isotopes, where the electron capture delayed fission probabilities depend exponentially on the QEC and fission barrier. No deviations from this trend were observed as a result. The cross-section for this experiment was around 6 nanopound. Then we have another finding lately. Actually, this was published this year by Kalle Auranen and co-workers. Here we are exploring the limits of nuclear landscape and beyond proton triplet nucleus. 211 protactinium was produced for the first time at the level of 20 picopan. If I'm not mistaken, this protactinium is the lightest isotope that can be considered as a very heavy element. So this is the lightest very heavy element ever produced. So in both experiments, we used beams intensities higher than 100 particle nanoamps. And after some of the upgrades related to the new, related to the K130 cyclotron, we will have these beams available again. And these are good examples of cases with rather low statistics. One can gain a lot of spectroscopic information at extreme, where other methods are not suitable anymore. Okay, so these are the new nuclides at MARA. What we have done, so this is work by Andy Briscoe and co-workers. So I'm here showing the two new isotopes that we have been found. Osmium-160 decays via, it has been two different alpha decays seeing, and then from the tungsten-156 goes via two branches of betas all the way down to here I should state that this identification again is based on the fairly long decay chain. Another example, Mercury-170, Platinum-165 by Joshua Hilton. Here, these are new alpha emitters. And then again, we have from the same experiment, 2C65 iridium and gold-169. For the latter, I should state that there we had to collect traces in order to distinguish between the decay products, because the decays were so fast. Now I'm moving to the in-beam work, and this is studying collectivity and shape phenomena in extremely neutron deficient lanthanum region, which is work by these spokespersons, Kostel Petras, Janne Sareen and Bo Södervall. And this is to study ground state shapes via rotational properties and the occupied single particle orbitals. This is essentially covering the gap between spectroscopically known nuclei and the proton emitters. And zooming into the region in more details here. And I'm not expecting you to see or to be able to read that, but what I want to show here is that this is essentially very rich region where there are suitable isomers for tagging. So I'm giving you a glimpse of what we can do with the good focal plane setup and a prompt spectrometer. So when gating on the isomeric transition here, which is marked with this orange bubble, all these level peaks that are seen on the right are identified. This is barium-119. This is a neighboring nuclei. We had several different masses delivered to the focal plane, so we could try tagging with different isotopes. These are just different examples of what you get when gating on known isomers. I should also say that, of course, we can do this vice versa. If we identify something in the prompt with the EUROGAM, we can always look back what happened at the focal plane and look for the isomers using that, and you especially use that to identify which could be the nucleus that had a certain isomer. This is, I think, the most recent experiment we did a month ago or so. We studied mirror energy differences in A = 43. Spokesperson Silvia Lenzi and Alberto Pozo. This is a nucleus where the low spin states are known, and here the focus was on mirror energy differences at high spin. So here on the left there is a level scheme of scandium-43. At slow spins, the structure is very known, and it can be interpreted as a cross-cell particle hole excitations from the SD cell. In the middle, I'm showing the gamma rays here. And now if you want to identify some of these by gating on again on the 152, which is isomeric state, you can identify nicely the isomers, the gamma rays that are built on top of that level. In a similar manner, we wanted then to see what we know in titanium. So again, gating on low energy, the low lying transition, we can identify these. I should note that there are, as you can already see from here, there are candidates for transitions that are here at the highest spin. So we are very optimistic that we are going to get a nice result out of this experiment. So let me move for the future prospects. So you see that we have a very rich campaign still ahead. This is the list of the pending proposals at the moment. Actually, I'm not even including all of the proposals accepted here. This is not including the results from the most recent pack that was in September. Nevertheless, there is more than 260 shifts waiting to be run. And this is essentially a pie chart, just how the different experiments are divided between different setups within our group. I will now show you a couple of slides that are not necessarily typical what we've been doing so far. So this is a proposal from Juha Uusitalo and Charamba Kujampatar. The motivation in the nuclear reaction dynamics studies as MARA. So the motivation for these studies could be declared as, first of all, in non-fusion, for example, calcium and curium reactions, new short-lived neutron-deficient isotopes of heavy elements have been synthesized due to the presence of very broad Z and N distribution of nuclei in the exit channels. And secondly, two well-separated energy components have been observed in nickel on lead and titanium on californium reactions, which could not be explained within the standard two-body collision kinematics. So therefore, one could argue that non-fusion reactions are not yet fully explored, and therefore we have a good potential to open up new territory for research at RITU and MARA. So this is an experiment that we hopefully will do quite soon. We are also now upgrading the RITU focal plane with the new setup, mainly to have the same versatility as we have at MARA at the moment. We will renew the implantation detector, which will have a 2 to 30% higher efficiency. And this will also have higher granularity. That essentially means in practice, Did I lose my video?
No, it was flickering, so you can turn it on again.
All right. Is it any better?
Yes, much better.
Okay, good. So yeah, the higher granularity will allow for the either it will allow for the higher beam intensity or longer searching times, and hopefully we can again achieve the 100 particle nanoamp beams and metallic beams available after the cyclotron upgrade. RITU has been serving us for a long time, and we are looking forward for getting back to action. Of course, MARA was the separator that we were also looking forward to get commissioned, and now it's been running very nicely for a couple of years, but there are still lots of experiments that we can do at RITU. This is another device, advanced Plunger-Particle detector array APPA. There is a push for experiments at MARA, where we would like to do lifetime experiments. We have had a very fruitful program on lifetimes in general, and this APPA is one of the devices that we are now developing. This is essentially combining the gamma-ray array together with the JUROGAM device, but also with a plunger. So we need plunger for channel selection in some of the cases as listed here, for example. And then this is something that we want to do to continue our fruitful conversion electron program. It's an old technique, Recoil-shadow method, to measure lifetimes of the zero plus states that has already been proposed in the 1970s. It sounds fairly simple, we have a beam hitting the target, and we can include a typical solenoid spectrometer, like for example, I showed you the shades. Here we would have the target behind a shadow, and those of you who don't know, whenever running conversion electron spectroscopy, there's a huge flux of delta electrons. So somehow we have to get rid of those. So in the Recoil-shadow method, the trick is to put a baffle here or a block, just physical block that will block the electrons, delta electrons that are of low energy. And then the nucleus of interest is still in its excited state before it decays until it reaches, it goes beyond the shadow, and then it emits a conversion electron that is being transported into the detector by the solenoid field. Then the recoil flies forward for the separator, and we can use the recoil-decay tagging technique for that. Yeah, it sounds fairly simple, but if it was easy, it would have been done already quite some time ago. Nevertheless, there is lots of nuclei that could be studied. For here I'm including level energy systematics and lifetime systematics from the LED region, where I'm plotting the first excited 0+ states and the known lifetimes. So I calculated that here we could have maybe around 20 cases to be measured, which fall into the region where this technique could be applied, which could be maybe to, say, nanosecond range. Of course, there is also a lower limit, which is considered to be around 100 picoseconds. So finally, I would like to show you the charge-plunger technique, which is now somehow closing the loop. This is again based on the conversion electron emission. So the very simple idea is shown in this plot. So we have a charge reset foil, and we have a nucleus in its excited states. If it emits a conversion electron after the charge reset foil before entering, I should actually put here a separator. Before entering the separator, the nuclei will be in a higher charge state. Whereas if the emission happens before the charge reset foil. So then again, by looking at the intensity balances between the low charge state recoils and the high charge state recoils, one can actually draw a curve as a function of target to reset foil distance. And based on these facts, one can actually extract a lifetime. There is a very recent paper by Lee and Popper, has been published in Nuclear Instruments Metals, and one of the day one experiments with this device would be naturally the Nobelium-254 that we have already shown that it's fairly easy nowadays to produce with our setup, but one should remember that there is actually not many ways to measure. The cross-section of Nobelium-254 is around 1 microsecond, which is micropound, which is too low in order to use conventional plunger technique, for example. However, we believe that it's nevertheless large enough for charge plunger technique. So in principle, you have to also remember that these low-lying 2+ states have a very high conversion coefficients. So this is also one reason why the traditional gamma-ray plunger technique would not be feasible in this case. So this is very interesting development going on. So I think this was the final slide. I want to lastly just show you the collaborators, and with this, I hope that I didn't miss any. And I would like to now just thank you for your attention.
Thank you very much, Janne. It's really nice to hear what is the suite of experiments performed at Jyväskylä. We have a bit of time for questions. Who would like to ask the first question? There is none in chat, but you can jump in if you have a question. I have a question. So what region of the chart are you on the n equals that? What are the next experiments to be performed along the n equals that line?
Sorry, you were asking that what are the experiments we will do next, or?
Yeah, for n equals that nuclei.
Maybe I will cheat a little bit and go to the list of pending proposals. In fact, we haven't set up the beam time schedule for the next year as of yet. We have lots of requests, as you can see. In fact, I cannot, I mean, there is no answer to your question. You see here the list of pending proposals. So there are, I think Krypton 70 is pretty much one of the experiments that are in the pipeline, but still it's not been scheduled as of yet.
Okay then. Oh, somebody else is saying that. So there is Thallium-176 produced by MARA. Okay, that's
yes, thank you.
okay. Okay then. Thank you. Any other questions? If not, let's thank Janne again with a round of applauses, virtual or live. Thank you very much, Janne.
Thank you.
The next speaker is from Canada. We haven't talked